where we've been. We know the force of gravity is equal to g, that constant, 6.67 times 10 to the minus 11, times the mass of the first object times the mass of the second object over r squared. And so you can use it to calculate the force of gravity. And I know we've talked about this before. In some ways, though, it's interesting. The force of gravity is equal to the mass of the person times the acceleration of gravity. And you'll discover that this equation works quite nicely. And if you plug in the mass of the Earth and the radius of the Earth, you'll discover that this equation gives you 9.8 meters per second squared, which in itself is good. But more interestingly enough, it will also tell you, for example, if you're out in space, a little bit further away from the planet, where r is now this distance, you'll discover that g gets smaller as you go further and further away from the planet. One other quick note about this, the units for g. Up to this point, we've been using meters per second squared. But there's another unit, which in many ways, when we're talking about fields. Now, you're saying, what is a field? Well, field is any area of space where there's a force being exerted. It could be an electrostatic field, it could be a magnetic field, or in this case, a gravitational field. And the way you write the units for a gravitational field is how much force something experiences per unit something. And so it turns out you could rewrite meters per second squared as 9.8 newtons per kilogram. And in some ways, this is actually a more elegant way of writing gravity. Think about it. It simply expresses what is the force of gravity in newtons on each kilogram of mass. 9.8 newtons per kilogram. If you have 2 kilograms, 19.6, etc. It works out really, really nicely. Big idea here is that g varies with distance. So take a quick look at this one. Let's say we wanted to figure out g at the moon's orbit. Now this is substantially further away. This is not to scale. There's the mass of the moon, there's the radius of the moon's orbit, and there's the mass of the Earth down below. How do we solve this one? Well, we can just plug and chug our formula, and you'll discover that, wow, the acceleration of the Earth's gravitational field at the distance of the moon is only this much. And I can ask, what's the force of gravity acting on the moon? This piece right here. And to do that, we could either use the full equation g m1 m2 over r squared, or we could realize, oh, it's just the mass of the moon times the acceleration of gravity at that distance. Plugging it in, we get that many newtons. And again, please remember, you could express the units for this as newtons per kilogram. And now, I asked a strange question. What's the moon's centripetal force? And you're like, well, wait, we haven't done any centripetal stuff. Yeah, again, remember, what is the definition of centripetal force? It's the net inward force required to keep an object moving a circular path. What is the net inward force acting on the moon? Well, yeah, it's the same number. It's this one right here. No big deal. What's the moon's centripetal acceleration? Well, to solve that, we can use this. Centripetal force equals the mass of the object going in a circular path times the centripetal acceleration. And we'll discover that, hey, wait a second. These two match. Yeah, it turns out for things in orbit, the centripetal acceleration is always equal to whatever the acceleration of gravity is at that point. Pretty simple. And then I can ask you, what's the moon's velocity? Well, we know the centripetal acceleration, so we can actually use one of our old centripetal acceleration equations that has velocity in it, and since we know radius over here, good old v squared over r might be a good choice. We know the centripetal acceleration, we know radius, and so if we plug this in, you'll discover that the velocity is about this, about 1,020 meters per second. We could have also used a different centripetal acceleration one, 4 pi squared r over t squared, and found the period of the moon. But you get the idea. The quick reminder as this one as well, how do you put an object in orbit? It turns out it's pretty simple. Again, if you shine a laser 8 kilometers, by the time you walk 8 kilometers, it'll be 4.9 meters above the ground. If you shoot a ball at 8,000 meters per second, remember horizontally, remember the horizontal velocity doesn't affect the rate at which it falls. What's going to happen? Well, in the 1 second, it would travel 8,000 meters horizontally. In that same 1 second, the bullet will fall 4.9 meters, the same distance any object would fall in 1 second. You're like, oh, wait, Ms. Clement, it does go straight and then it falls? No, in reality, what's going to happen is it's going to follow the curvature of the Earth. And it will stay at that exact same height. Still going 8,000 meters per second, but yeah, in reality, you can never do this at the Earth's surface because of air resistance. So if we just simply put it up out of the atmosphere a little bit, you can repeat this experiment with it just going in orbit forever. So here's the big idea. For an object in orbit, the net inward force, the centripetal force, is provided by the force of gravity. And you see this other box down here. Hold on, I'm going to fill that in. And so what's the centripetal force? It's just going to be the centripetal acceleration times the mass of the satellite. That's this piece. And the gravitational force is this piece, this whole thing right here. Notice that the mass of the satellite occurs on both sides. So we can cancel that out. And if we did, we get this. The centripetal acceleration is equal to this. But you might remember this is actually the equation we used just a slide or two ago for g. So what else is true for things in orbit? The centripetal acceleration is equal to the acceleration due to gravity at that distance. So you can use either one of these ideas when you're calculating orbits. So we're coming up here, we've got a couple of sample problems just to show you how it works. Geosynchronous satellites orbit the Earth with a period of 24 hours. If the mass of the Earth is that, at what radius must they orbit? So how do we solve this one? Well, starting out here, we start out with centripetal force equals gravitational force. And so you can quickly plug it in. Notice that I forgot to give you the mass of the satellite. Turns out it's irrelevant. Why? It's going to cancel out here in just a moment. But because I know the period and I'm looking for radius, there are multiple centripetal acceleration equations. I'm going to use this one. Why? It's got radius and period in it, so it makes it easier to solve this one. Getting rid of the mass of the satellite, we get this. And now I'm going to go ahead and solve for the radius, which is what the variable I'm trying to solve for. Gives me this. You're like, oh my goodness. Yep. Plugging in the numbers, 1 day is 86,400 seconds, 24 hours. G, mass of the Earth, period squared, all over 4 pi squared. And if you remember to take the cubed root, don't forget, you should get that r is equal to about that distance. Which is a fairly substantial distance, not to this scale. It turns out to put a satellite in geosynchronous orbit, it needs to be about 7 Earth diameters away. It's quite a ways away. Or is it radii? Take a look at this one real quick. The International Space Station orbits at an altitude. What is altitude? Altitude is how far you are above the surface of an object. So in this case, this is 100 kilometers. So be careful on this one. When you see altitude, it's how far above the Earth's surface you're at. So doing the same sort of thing, but what equation do I want to use this time for centripetal acceleration? Well, I've got radius, and I'm looking for velocity. So yeah, you might have guessed already. I'm going to use the old v squared over r for centripetal acceleration. What's the big idea here? You can plug in whichever of the equations we have that's most convenient. Mass of the ISS is actually going to cancel out again, just as you can sort of see. And if we solve this one, we get that. And then rearranging to solve for velocity, I just have to multiply both sides by r, and I get that. And then plugging in our numbers, mass, or g, mass of the Earth, radii. Now notice this. It's the radius of the Earth, which I gave you before, plus how far above the Earth's surface it is in meters. 100 kilometers, 100,000 meters. Notice it's not squared because I got rid of the squareds over here. If you solve this, you'll discover that the International Space Station is going about 7,850 meters per second. You might say, wait a second, didn't you just tell us to put something in orbit? It was 8,000 meters per second for the Earth? Yeah. But guess what? G is a little bit smaller at the altitude of the International Space Station's orbit, so the velocity is just a little bit smaller as well. Take a look at this one. Pluto, the minor planet, has a moon named Charon that orbits with a period or radius of that and a period of that. Based on this information, could you please tell me the mass of the planet Pluto? You're like, what? Yeah, same idea. We've got an orbit here. But we're trying to find the mass of Pluto. We've got period and we have radius. Which equation am I going to use here for centripetal acceleration? Well, I'm going to use this one, the 4 pi squared r over t squared. Mass of Charon actually is not critical, the mass of the moon, to find the mass of Pluto. Rearranging this to solve for the mass of Pluto gives me that. Plugging in our numbers, we get that. And solving it, we get something around that, which is approximately right. It's really close, within about 10% or so. On your worksheet for tonight, you've got a couple of problems. I just want to do one of them with you. They're all dealing with orbits. Take a look at this. The Earth has a mass of this and a radius of that. National Science Foundation wishes to place a satellite in circular orbit to measure planetary deforestation at an altitude, notice, be careful of that word, of 160 kilometers. That's the distance in the Earth's surface and the satellite, not to scale in the drawing. What's the gravitational force in the satellite? That's a plug and chug. Notice again, though, take a look at the radius down below here. This is r squared. This is the radius of the Earth plus the satellite. Interesting. I wrote down the wrong radius here. It should be 6.37. I put it right here. Sorry. 160 kilometers becomes 160,000 meters. Plugging it in, you'll find the force. I'll let you do that. BS, what's the work done on the satellite during one orbit? Well, we know the force of gravity is acting downward, and the velocity of the satellite is tangential to that. If you remember, the definition of work is force times displacement times the cosine of the angle between it. At each moment, tell me something about the displacement and the angle between it, and you should realize, wait a second, at every single instant, the angle between the force and displacement is 90 degrees. From there, you can actually calculate the work done. If you remember what the cosine of 90 degrees is. What's the centripetal acceleration of the satellite? Well, I'm going to use this because I already know the net inward force. Like, what? How do we know the net inward force? Well, that's going to be the force of gravity. Yes, I could have also just figured out what the acceleration of gravity is at that altitude and used that to solve it. But since I already had the force of gravity, we can just plug it in. Force of gravity, 4,680 newtons. Mass of the satellite, 500 kilograms. The centripetal acceleration, 9.35 meters per second squared. And yes, that is also equal to g at that altitude. A little bit less than 9.8 because we're a distance above the Earth's surface. Finding the period. Which of the centripetal acceleration equations have period in it? There's a couple of them, but in this case, we know the radius. We know the centripetal acceleration, so probably this one. And plugging in our numbers, we know that centripetal acceleration is this. Radius, again, notice the sum of these two, the Earth's radius plus the altitude, all over t squared. And if you solve it, you'll get a period of about that, which is about 90 minutes, give or take a little bit. And then E, what would happen to the period if the mass was doubled? And this one I'll let you think about. If we made the satellite twice as massive, what would happen? And show your calculations. I'll let you try that. Real quick note on this one. Gravitational potential energy, U sub G, is equal to mgh. And this is perfectly fine. For example, if you lift a block from the floor up to a tabletop, no big deal. G doesn't vary all that much if you're just lifting something up, say, for example, a couple of meters. But on the other hand, we run into an issue. if you're taking something off the planet and up into orbit, g is no longer a constant in this equation. In fact, remember the equation we had before? So let's fix it. Whoops, we're in the same spots. G is no longer constant for astronomical distances, so what are we going to do? Remember, G is equal to this from an earlier slide near the Earth. And so we can plug that into our equation. So mgh becomes m, this expression, times h. But if you think about it, when we lift something up, what is the height that we're lifting it to? Well, typically it's actually the radius. Oh, I actually drew it on there. And so what happens to this equation? It becomes simply this. Now, one quick note on it. You're like, where'd that negative sign appear? You might remember way back when I told you that there is a point where we defined gravitational potential energy. It's zero when you're at infinity. And so if you fall to any orbit from infinity, you're actually losing gravitational potential energy, which means at every point in the universe, we have negative gravitational potential energy. Don't let the negative sign disturb you too much. Not meant to be too profound, but this is a more general form of gravitational potential energy. This one's fine near or at the Earth's surface. This one is valid everywhere, including if you lift things up. You're like, Ms. Calmer, would this also work at the Earth's surface? Yeah, you would just figure out the gravitational potential energy at the floor, the gravitational potential energy at the top of the table. R would increase by 1 meter, and you would find the difference and figure out the change in gravitational potential. But it's a big idea. Next slide, real quick on this. So we now know the general equation for gravitational potential energy. And we know kinetic energy, the energy of motion from pre-4. An object in orbit has both gravitational potential energy and velocity. Take a quick look at this. We know for orbits this has to be true. And I'm going to use v squared over r for my centripetal acceleration this time. M sub sat is the mass of the satellite. And if you solve it, you'll discover for something in circular orbit, it's just velocity is that times the mass of the Earth over r. And the kinetic energy is going to be 1/2 mv squared. V is equal to the square root of this, so the square of it's without that. And so we end up with the kinetic energy equaling to this expression. So this is the kinetic energy of a satellite in orbit. You're like, okay, yep, going with it. So what's the total energy of something in orbit? Well, it's the sum of the kinetic energy, which is the equation we just found right here, plus the gravitational potential energy, which we have here, and we simply plug in the values. If we do a little bit of algebra on that, watch what happens. We got that. Common denominator, multiplying the second equation through by 2/2, you'll discover that this is it. For any object in orbit, its total energy is simply given by this expression. And yeah, AP actually would like you to know this one. One quick note, notice that this is exactly 1/2 of the gravitational potential energy. You're like, what? Oh, yeah. It's just gravitational potential energy is over 2. This is just 1/2 of that. In other words, the energy of an orbit, there is still a deficit of energy. It would take energy to help this orbiting object to escape, but it's trapped in orbit and its energy is roughly given by that. Don't panic about this too much. It's not used a lot, but I just want to show it to you. Escape velocity is actually interesting. If you think about it, a couple of quick notes. For a circular orbit, we already know the equation. That equation was what we just wrote a moment ago. G times the mass of the thing, or mass of the planet, all over r squared. Um, oh, sorry, over r. My bad. Um, but if you go a little bit faster than that, as long as you don't go too fast, you'll end up with an elliptical orbit, one that looks more like this red circle. And I want to quickly talk about this. Um, so what's the escape velocity? Escape velocity is the minimum initial velocity that an object must obtain in order to escape from the gravitational field of another object. The object's kinetic energy must overcome the deficit in gravitational potential energy, the equation we had before. Escape velocity does not depend on the mass of the object. However, heavier objects will require more energy to escape. So mathematically, let me show you real quick. Let's say we've got this rocket, 1,000 kilograms, trying to escape from the Earth's surface. Mass and radius of the Earth given below. What has to happen? We've got to give it enough kinetic energy so that it overcomes the deficit in gravitational potential energy. Kinetic energy, I'm going to call the satellite M2 and the mass of the Earth M1. Kinetic energy of the satellite or rocket ship 1/2 m2 times v squared. The gravitational potential energy, negative g m1 m2 over r. Doing a little bit of algebra, just moving this term to the other side, we get this. Mass of the satellite, or mass of the rocket, notice cancels. And we can very quickly calculate, if you plug in the numbers, to escape the Earth, you need a velocity of 11,200. You're like, wait, didn't we solve it as 8,000? Yeah, it turns out 8,000 is the velocity you need to go in a circular orbit. But if you want to escape the planet entirely, leave the solar system, you need to be going at least that fast. What happens if you go in between these two speeds? That's where you get the elliptical orbit. Less than 8,000, crash. You're not going to be in a circular orbit. More than 11,200, you'll escape the Earth. What happens if you go in between there? You'll end up with an elliptical orbit. You'll move away from the Earth, but not quite escape it and fall back towards it. Here's the escape velocities for a bunch of other objects. You can sort of see it. Don't worry about the time dilation. But notice for the Sun, the escape velocity is much larger. Earth, the number we just calculated. Pretty easy to get off of some of these planets, like Pluto, not too fast required. But some of them are quite large. And so you can sort of see it. And again, we sort of talked about this. Escape velocity, here's the general equation, has to be greater or equal to, here's the equation we used before, 2gm over r. And just so you can sort of see the relationship, here's for circular orbits, centripetal force times mass equals that. What's the difference between these? This is for a circular orbit. This is escape. What's the difference? Yeah, this one's just larger by the square root of 2. It's got a 2 in the radical up on top. So 8,000 meters per second is velocity for orbit. If you take that times root 2, you get that 11,200 meters per second, the escape velocity. Last thing I want to hit on this chapter real quick are Kepler's laws. Kepler's law is fairly simple. First law, and this one took him 20 years to come up with, Kepler was convinced that planets didn't move around the sun in circular orbits, that they actually traveled in a different shape. And so he had data and worked with it, and it was really incredibly hard data to work with from a moving Earth. He looked at Mars, and discovered that the planets move in ellipses around the sun, with the sun at one of the two foci. For those of you who remember your ellipses have two foci. The sun is at one of, I didn't put that one very well centered, it should be over a little bit further, with the sun at one of the two foci. Most of the planets do not move in this strong of elliptical orbit, but notice one thing here. As it falls towards the sun, the velocity of the planet gets larger, and as it moves away, it slows down. Kepler's second law allowed the prediction of a planet's position very, very accurately. For planets in elliptical orbits, he discovered that planets would sweep out equal amounts of time, or equal space and equal time. You're like, wait, what are you talking about? Well, a planet moves slower when it's further away from the sun, so it only might move from here to here in 1 month's time. Kepler's second law stated that the area here should be equal to the distance that the planet moves when it's close to the sun, which would be, it's moving faster, it probably sweeps out a larger area here. He said these two areas are always equal. He had no idea why, but it turns out there's something called angular momentum, which we'll talk about in another chapter. And it turns out angular momentum is equal to r times m times v. And so you can very quickly calculate this one, but he didn't know why. His third law states this. Don't overwhelm yourself. The square of the orbital period of a planet is proportional to the cube of the semi-major axes of the orbit. You're like, what? It turns out, remember for ellipses, this distance right here is the semi-major axis. It turns out the length of the semi-major axis is the average radius of orbit from the sun, which is at one of the two foci, to the planet. You're like, wait, why does this work? It turns out, again, Kepler didn't know this yet. Kepler preceded Newton. Once you plug it in, you could sort of see it real quick here. Oh, yeah. G is constant, mass of the sun is constant for all the planets. That's what they're all orbiting, over 4 pi squared. And yeah, sure enough, r cubed is proportional to t squared. You're like, great. So for objects in orbit around the sun, we know this is true, and it turns out you can figure out the constant. The radius in meters cubed is equal to this constant times the period in seconds squared. That's pretty nice, but it turns out there's a much more elegant way of solving this one for Kepler's third law. If you measure the distance in astronomical units, you're like, whoa, what's an astronomical unit? The astronomical unit is the average distance between the sun and the Earth in its orbit. That's an AU. Not to be confused with atomic unit. It's used in chemistry. If you measure the radius in astronomical units and the periods measured in years, the equation becomes much simpler. The constant's just 1. So, for example, let me show you how you could solve that. Jupiter orbits the sun at a distance of 5 astronomical units. What's its period in years? Plug and chug. 5 in radius is 5 AUs. We're looking for the period. The constant's 1. And you'll discover that Jupiter orbits with a period of about 11.2 years. So nice. A brain breaker here real quick. I'll just throw it in real quick. All the vertical straight lines in this block-lettered word have been removed. Mentally picture where those lines should be to figure out the word. Pause if you need to real quick before I give you the answer. But yeah, it's imagination. Couple quick notes on this one before we get done. Escape velocity is given by that equation. Real quick question. Is there a maximum possible escape velocity? What happens if you exceed that value? Is there a maximum velocity? And it turns out, yeah, there is. A small letter c, which is the variable we use to represent the speed of light. Nothing can go faster than the speed of light. So what happens here? It's possible for an object to have an escape velocity greater than the speed of light. And since nothing can escape that, at that point, we've got a problem. We've got an issue. What do we have? We've got a black hole where even light moving at the speed of light can't escape it. And so take a quick look at this. Here's our equation for escape velocity. I made it equal instead of greater or equal to each other. We're trying to figure out when the escape velocity is equal to the speed of light. Rearranging that, squaring both sides, and then solving for the radius, we get this. What's this the radius of? It's the radius of what we call the event horizon, the point of no return. This is actually not a point in space, but what it is if you're closer to the center of the black hole, the singularity, than this imaginary radius here, you can't escape. Inside of here, V escape is greater than C. That's impossible. You can't get out. Outside of the event horizon, the escape velocity is still less than c. And so you at least have a possibility of escape. The event horizon marks the imaginary point in space. Once you cross it, it's hopeless. You abandon all hope. Real quick, that's for a non-rotating black hole. We actually think most of them rotate. Um, this is a Kerr black hole, rotating one, and you can quickly read about it, but it's not that critical. And then I've just got two quick AP problems. Well, you can take a look at those on your own. This one, initial velocities this way, angular acceleration is going to be this direction. What's going to happen? Real quick, if you do your right-hand rule, you'll discover that the initial omega is positive. It's pointing in the positive z-axis out of the screen. And it's going to be slowing down, stopping, and then starting to unwind because this force is greater than this force. Which graph is the correct one? I'll let you think. Pause here if you need to. Correct answer on this one should be C. And then this one was a real challenging one. The Earth-Moon system actually is in orbit around each other, around this center of mass. And so if you looked at the Earth and the Moon as they orbited the Sun, it would actually do this really cool pattern. They're both rotating around their center of mass. The question is, which of the following arrows best represents the acceleration of the center of mass of this double planet system when it's at this point? You're like, what? What? A lot of students freaked out on this one, but what's the correct answer? Well, it's just the force of gravity acting on it, which is acting this direction, which means the centripetal acceleration is also acting in this direction. What's the correct answer on this one? It's A. Hey, good luck with your homework tonight. You should be in good shape. We'll talk to you soon.